I'm Jonathan Aldrich, and let's talk about constructing ASTs with action routines. An action routine is a function that the compiler writer instructs the compiler to execute at a given point during parsing. Generally, action routines enable the AST to be constructed during parsing rather than constructing a parse tree and then translating it to an AST, which can be a laborious process. Let's look at an example here shown on the left. Here we have a grammar, and each production has an action routine associated with it at the end of the production. For example, when we parse an expression as a term, we return that term t. Let's start at the bottom. When we recognize an add op or a mult op, the grammar says that the add op can be plus, minus, and if it's plus, then we have an action routine that returns plus from parsing this addition operator. That is then used when we parse expressions. So the expression parser, which is for addition operators, that's the second production in this grammar. We've expanded a little bit since our original grammar, right? Our original grammar says that an expression can be an expression followed by an add op followed by a term. But here, we've taken the expression and we've said, well, that expression will return some tree, t1, and then add op will return some operator, right? It'll either be plus or minus, according to which production we used. And then t2 will return a term. And so then, based on that, we have an action routine that says, let's return an abstract syntax tree, which is a binop of t, op, and t2, combining these two. So in general, what we can do with action routines is we can bind the result of parsing other pieces of the grammar to variables, and then we can use those variables in an action routine to return a tree for this current expression or whatever we're parsing. Let's look at an example of AST construction using action routines. Here we have a figure from the book, and we're going to start with part A, where we build up the lowest level piece of an expression. We're looking at the expression 1 plus 3. And so 1 will be identified first as an integer constant. You can see that here the int const refers to the value 1 as the integer constant we have identified. Typically, this int const is part of our AST, and 1 is the token that int const corresponds to. We then recognize a factor, and then that factor will return an int const. We return that to term. Term returns that to expression, and then expression refers also to this intlit of 1 variable that we generated when we parse the factor. Similarly, we can parse the factor for int const of 3 in the same way. We're identifying an integer constant, and then when we parse the factor, the action routine will create an intlit data structure, which we then return as the term. Putting these together, in part B of the diagram, we take the expression and the term from here down below. We've parsed an add op, which will return the plus, and we put these together, right? We take the intlit from the expression, the other intlit of 3 from the term, and we take the add from the add op and put these together into a binary operation. Now maybe this 1 plus 3 is part of some larger expression, 1 plus 3 times 2. And so let's go to part C here. We're going to take the thing we already parsed, the term of the binop of intlit 1 plus intlit of 3. And again, we'll identify an integer constant of 2, create a intlit AST for 2 here, and then when we parse the term times the factor, we will create another binary operator using these 3 parts. The big part we have from the previous slide, the little part of intlit 2 that we just created, and then the times operator. And so we end up with this AST as the final result. So in LL parsing in particular, action routines can appear in the middle of grammatical rules. This is not possible in LR parsers, because in an LR parser, we basically have to read all the symbols related to a production of the LR parser before we recognize that production and can therefore take some action based on it. But with LL parsing is predictive. We always know from a look ahead of 1 which production we're going to take. And so anytime after we've identified the first symbol in that production, we can have an action. And this is actually useful because of the limitations of LL parsing mean we can't go strictly bottom up in terms of constructing the parse tree. We have to go top down to some extent too. To see how this works, let's look at the rule for expressions. So an expression in our LL grammar starts with a term, and so we'll build up a term and get the AST for that term, put it into T1. Then we'll have term T2, which will be the term tail, right? So remember, for parsing expressions in an LL grammar, the term tail will either be empty if the expression is just a term, maybe it's just a multiplication of two things, or we can have the term tail be an addition operator like plus or minus, followed by another term. So in our term tail, we're going to have a couple of different action routines. So one, if we get the add op, then we will construct a term T3, which is constructed from the add op and the second term T2. But where did the first term come from? Well, that was parsed up here in expression. So expression parses term T1, and then it parses the term tail T2, the term tail, but we have to pass T1 into it. And then the term tail will construct the overall term. Okay, so term tail takes the term from the first part of the addition operator, of the addition operation. It'll take the operator op and the term T2 and put them together. T3 equals binop of T1 and T2, and then we'll return. And then we might have another term tail, right? We might continue on reading more terms. And so in this case, whatever that final term tail returns will be T4. Now there is a base case for term tail where we've done evaluating everything. In that case, we just return the term T1 that we already parsed. So the idea in LL parsing at a high level is that each term produced in the first part of an expression can be passed down to the rule that parses the second part, and then that rule creates the AST element for the higher level expression. You can see this in term tail, which I just outlined, but if you look lower in the grammar, you can also see that in factor tail. So things are a little bit more complicated in LL parsing just because the structure forces us to pass these expressions down to do things elegantly. The good thing is that we can do that, right? Because we can have action routines kind of in the middle of a grammar and then take the result of that, T3 in this case, and pass it to another term tail because we have predictive parsing. And so as soon as we read one thing, we know which case of the grammar we're in. Action routines can also be embedded in recursive descent parsers. What this effectively means is that we're just going to return, the AST that we create. And in fact, a recursive descent parser corresponds to an LL grammar. And so here I've shown the implementation of term tail in a recursive descent parser. In this case, we have the left-hand side, the part that's already been parsed in our AST. And if we get an input token of plus or minus, that means we're extending this by adding something more to it. In that case, we will take an add op, which will be a string, either plus or minus, and then we'll call term tail again, but we'll call it by passing a binary operation that has the original left-hand side, this operation that we just parsed, and a recursive call to term to parse that piece. Otherwise, if we get another set of start symbols, such as close parentheses, ID, read, or write, then we're done parsing this expression, or this term, and so we'll just return the left-hand side that we already got. If none of the tokens matches what we have a parse error, which is just as we showed before with recursive descent parsers. So it turns out that action routines may do substantial semantic analysis, not just construct an AST. And this is a fairly common thing to do in very simple compilers. In this case, context from other parts of the program might be needed. For example, we might need to know what the types of variables are that are currently in scope. And so this can be passed in using an idea called attribute grammars. Attribute grammars are discussed in the supplement to the text, section C4.6. And the formalism there generates action routines to pass appropriate context both up and down in the grammar to support semantic analysis. A one-pass compiler carries this further, not just doing semantic analysis in the action routines, but actually generating output code. And so the thing returned will not be an AST, but the actual code for the program. This is historically an important technique, as the whole program could not fit into memory. And so basically returning, in fact, instead of returning, we would actually write to a file. This approach is now used mostly for simple languages because we generally do have enough memory to fit the programs we're compiling. But more complex languages typically wouldn't use this technique because it's a cleaner approach to use a nice AST representation, and so the action routines will just compute an AST, and then we'll separate out the more complicated analyses necessary for a more complicated programming language to be done on that AST as later passes. Let's check our understanding. Why can't action routines be placed at arbitrary locations within the right-hand side of productions in an LR context-free grammar? To answer the question, in an LR grammar, the parser can't in general recognize which production is being used until it has read all the symbols that can be used on the right-hand side. So actions can only be triggered when the complete production is recognized.